In this lecture, we're going to talk about the limits of piecewise defined functions. Hopefully you remember what a piecewise defined function is. We've seen some in the previous lectures, and here's a great example of one right here. You're going to recognize a piecewise defined function by this opening curly bracket right here, and by the fact that there are multiple pieces which define the function. So for example, maybe I want my function to be x squared plus 1 over x when x is less than 2. And then I change my mind. Maybe I want f of x to equal x minus 2 when x is greater or equal to 2. Okay? Let's just do a little bit of quick review first. See if you can give me the values for what's f of 1 and what's f of 2. Okay, so this is a review from pre-calculus. Keep in mind that when you have these multiple pieces of the definition, you're just looking at what's the input, and then you're going to go over here and say f of 1, well, which of these cases does 1 count as? Less than 2, right? So then I will put it in the instructions for all things that are less than 2, which is 1 squared plus 1 over 1. So the answer, f of 1 is 2. What about when I'm asking to put in the number 2? Which one are you going to use? You have to look for the one that has the equal sign under it right here, right? So then I'm going to plug in the number 2 into this, so I'm going to do x minus 2, and so f of 2 is 0. Okay, so that's a piecewise defined function. Do you guys remember how we can approach the graphs of these types of functions? Some people might know their graphing calculator well enough to be able to enter both of these pieces in. But if you just know the basics of your graphing calculator, then what you need to do is separate your drawings on either side of this point right here. This is what I'm going to refer to as the breakpoint. The reason I call it the breakpoint is because the number x equals 2 is where we decided to say, stop, I don't want to do that anymore. Now I want to do this instead. Okay, so that's where we broke the definition and decided to put in something new. So if you hear me say breakpoint, that's what I mean. It's going to be the number at which we changed our mind on a piecewise defined function. Okay, so how can we approach this graph? We have to say, well, when x is less than 2, I want to graph this. So then put that in your graphing calculator, and the calculator will probably say, looks something like this. Okay, so you draw it, but then when you get to 2, you stop. Stop drawing it. Now, when x is greater than 2 over here, now I'm going to ask my calculator, what does that function look like? And it looks like something like this. So you draw like that, it's a line. And then one more thing is, which one is the open hole and which one is the closed hole? The open hole is when you don't have the underlined thing here. That's right. So see, it doesn't count as that when x is equal to 2. The closed hole is the one that does have the underline right there. So that's going to be the closed hole, and that completes my picture. Okay? So let's talk about the limit of this piecewise defined functions. Very important for piecewise defined functions, consider each one-sided limit. Okay? Anytime you see a definition like this, even if I haven't asked you to explicitly, consider each one-sided limit separately and then make your conclusion about the overall limit. Okay? So let's consider the limit from the left of f of x, and then we'll consider the limit from the right of f of x, and then we'll make our conclusion about the overall limit. Okay, so from the picture here, it looks like if I'm sneaking up on the number 2 from the left-hand side, so I have numbers that are less than 2, what number am I approaching? Now, if you have a graph, you can probably approximate this number, but remember, graphs are just to help you along. They are not where I want you to derive your actual answer. I want you to use the analytical method, which is to take the number 2 and plug it into this function. Why am I plugging in the number 2 into this function when it says I can only plug in things that are less than 2? That's because I'm thinking of the concept of a limit. Okay, I'm trying to think of things that are very, 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 very close to 2. Really, ideally, if I had enough time, I would plug in 1.99999, 1.9999999, etc., and I would get closer and closer and see what my outputs are. Okay, but if I just wanted to approximate that, I'm getting very, very close to 2, right? So I'm just going to throw in the 2 here, okay? So that's why I'm allowed to take the 2 and put it in here, is because I'm trying to approximate the behavior of the function as it gets extremely close to that value, even though technically it's less than it. So then I get 2 squared plus 1 over 2, so that would be 4.5. And if you saw it on your graphing calculator, you probably guessed that this height was around 4.5, but maybe you weren't sure if that was exactly the answer, and now I know it's the answer, and that's because I plugged it in right here. Okay? I plugged it in here once again because I'm being asked for the limit from the left. That's why I plugged it in to the part where it says values from the left, values that are less than. Okay? Because now you're going to see me take the same number 2 for this one and plug it in to this equation over here, because now I'm coming from the right. Okay? Now it turns out this is also true for equals, but even if this equal wasn't here, just like the equal wasn't up there, because I'm considering the limit as it approaches a number from the right, those numbers will fall into this category. 2.0001, 2.00001, those all fall into here. So to get a feel for what the function's doing, I'm just going to throw the 2 into here. So I'm going to get 2 minus 2, which is 0. And so, just like the graph confirms, I get 0. Okay? So that's how you would find both one-sided limits on a piecewise defined function. And then, even if I haven't asked you that, if I'm going to ask you what's the limit as x approaches 2 overall for this f of x, what's your answer going to be? Does not exist. That's right, it does not exist because these two one-sided limits do not agree. If they did agree, then the answer would be the value that both of them agreed on. But because they do not agree, even though both of those exist, the overall limit does not exist. Okay, let's try a little bit more challenging of a problem here. For piecewise defined functions, now I'm going to give you a little puzzle to solve. Okay? Let's say that I want to define a piecewise function f of x, and I'm going to say that it's equal to 1 over x squared when x is less than 3, and I'm going to say it's equal to a value a when x is greater or equal to 3. I hope this isn't confusing you, but right now I'm putting a placeholder here, a, where a represents any real number. Okay, now you also saw this a before when I defined limits and I said the limit as x approaches a. That's not the same. Right now the a is representing an output of a function, as opposed to when the a is here, it represents the input of a function. Why do I reuse a? Because it's very common. It's common practice to have the letter a represent what we usually call a parameter, which is just any real number. Okay, so a is some real number. Alright, so a is some real number here. And what a represents in this context is a is the real number, which is the output of the function when I put in numbers that are 3 or greater. Okay, so this is no longer the picture of the function. My question here is going to be, what value of a should I put that would make the limit as x tends toward 3 overall exist? Okay, so that's my puzzle question to you, is what value of a will make the limit as x tends toward 3 of f of x exist? Well, we just saw in the last example that when one-sided limits do not match, the limit overall does not exist. So now I'm giving you a little puzzle. I want you to consider yourself, what are both of the one-sided limits? And then, what is the value of a that would make that limit exist? You're going to have to match, put in a value of a that matches the other one-sided limit so that the overall limit exists. Little puzzle problem. Okay, I will attempt to draw this in case you're curious about what this looks like. 1 over x squared kind of looks like this, right? And here's x is equal to 3. Now that's not the value when x is equal to 3. Okay, so I've drawn the left-hand side of it because I've been given 1 over x squared, but for the right-hand side, I don't know. That's the question. Should I make a up here, like this maybe a equals 7? Or should I make a down here, so a would be like minus 1? I don't know which a to choose. So you have to pick the value for a that matches. And what am I trying to match here visually? What am I trying to match? The height, that's right. I want to pick a value for a that matches what's happening as the function approaches 3 from the left-hand side. Okay? So let's write down the one-sided limits because we know that we have to figure those out first to make any conclusion about the overall limit. Alright, so let's see. What is the limit as x approaches 3 from the minus side? How do you find it? Well, when x is less than 3, but it's very, very close, that means I'm in this category because x is less than 3. But it's so super close to 3 that I'm going to eyeball what it's going towards by just putting the 3 in there. Okay, and when I do put the 3 in there, I get 1 over 9. And if you graphed the function 1 over x squared, you see that around x equals 3, the height is 1/9. Right? Now, what's the limit as x approaches 3 from the positive direction? Well, that would put me in this category over here, right? Because I'm greater than 3. And what I'm saying here is it's always outputting the value a. Okay, well, I can't say any more until I pick a value for a, so it's just the answer is going to be a, whatever you pick. Now, do you guys know what to pick for a? The answer of what's the value of a? 1/9, exactly. You want to make these two things match. You want them to be equal, so you're going to make a equal 1 over 9, so that the overall limit as x tends toward 3 of f of x is going to be equal to 1/9. Okay? That's the answer to the puzzle. Okay, so that's just a little bit of fun, but how about some applications? Because we're in business calculus right now. Let me give you a little application problem. And it turns out that piecewise functions are very common in business. You saw them in Math 147 when I started to talk about pricing, maybe like at the post office, the way that they price the postage based on weight, or if you want to make a deal for customers, a bulk discount, you might make a piecewise function. If you buy 10, then the price goes down. These are very common types of functions, and here's another application example, which is going to be tax season 2, tax brackets. Okay, so tax season soon. So let's say we have some different tax brackets, and let's let x equal your income level, and let t of x equal the tax amount. Okay, so if I make x amount of dollars, then I'm going to have to pay t of x taxes. Alright, now let's see how we will define our t of x. Let's say that the tax amount is equal to 0.10 times x if x is less than 10,000. So x is going to be in dollars. Okay, what this is saying here is that if you made less than $10,000, you have to pay 10% in the taxes. That's what that's saying, right? Now, what if I make a little bit more? What if I make inside this bracket between or greater than or equal to 10,000, but strictly less than $50,000? Then I'll have to pay $1,000 plus 0.15 times x minus 10,000. Sorry, this is getting a little squishy. Okay. Alright, so now if I'm in a little bit higher bracket where I make between $10,000 and $50,000, including the 10, then this number is going to calculate my taxes. Now, what this equation represents is it's the $10,000 that you had to pay on the first, this is the $1,000 of tax that you had to pay on the first 10 grand that you made. Okay, so if I made $10,000, I have to pay 10%, which is $1,000. And then, since I'm in the higher tax bracket, now I'm getting charged 15% of all the money that I made that was larger than $10,000. Okay, so let's say I made $35,000. I'd have to pay 10% on the first 10 grand, and then on the next 25,000, I'd have to pay 15%. That's why we have x minus 10,000 here. This 10,000 matches the top end of the previous bracket. Okay, and you're going to see that pattern continue. Let's say if I made more than or equal to $50,000, the tax would be $7,000 plus 0.20 x minus 20,000. Or sorry, 10,000. X minus 10,000. Okay. Oh, sorry, that's supposed to be a 5 there. That was a little typo. Okay, so going on with this understanding, the amount of tax that I'm going to pay if I'm in the high tax bracket, I made more than $50,000, is I have to pay 10% on the first 10 grand, which is 1,000. Then I have to pay 15% on the next 40 grand, and that comes out to 6,000. That's why I have the 7,000 there. And then I have to pay 20% on all the amount that I made over 50,000. Okay, this is similar to how taxes are computed in real life, is that you have to pay different percents on the different amounts that you pay in each bracket. Okay, so we have a function here. It's a piecewise defined function. Let's play with the limits a little bit, and let's see if this seems like a fair way to compute your taxes. Is this fair? I put fair in quotes, because what's really fair when it comes to taxes, right? So what I mean by fair is like if I graphed this function, and let's say here's the $10,000, here's a $50,000 line. Okay, this is the amount of tax I have to pay, that's how much money I made. If I graph this function, I wouldn't expect it to make any funny jumps. That wouldn't be fair, right? Like if I made $9,999, I have to pay a little less than $1,000. If I make $10,001, I have to pay a little bit more than $1,000. There shouldn't be any crazy jumps when I graph this function. That's what I would call fair. Okay, so what I'm going to do is I'm going to graph this piecewise function, and I would encourage you to do this yourself. These are all linear functions right here. You should be able to form this graph yourself. And it looks kind of like this, and then it makes a jump, and then it makes an even higher jump. Try to draw that a little more accurately for you. The slope is increasing little by little. It's very subtle, a little bit hard to see, but this is the $1,000 line, and this is the $7,000 line right there. Okay? I didn't see any jumps. When I graphed it, I didn't see any jumps, so I'm going to say, yeah, that seems fair to me. And another way to test that, whether or not there are jumps, is going to be to check the limits at both the breakpoints. Now, I'll just consider one breakpoint for the sake of time, but really, when you have a piecewise defined function, you should always be checking what is the limit, what is the overall limit at each one of the breakpoints to make sure that that limit exists, and therefore that the function, what we'll say later, is continuous. Okay? So let's try the breakpoint of $50,000 right here, and you could have done exactly the same thing for the $10,000 line. Okay, and this is going to be our final example on piecewise functions, so why don't you just jump in and see how much you can do with that without me saying any more. So go ahead and pause the video. And hopefully what you thought of to do was that you first have to consider both one-sided limits. I didn't say that, and might not say that on my assessments, on the tests, but really what you need to understand for piecewise functions especially is that you have to consider both of these one-sided limits first before you make your conclusion for the overall limit, okay? So that was like the secret question. This is really what I was asking. If they match, that will be the answer. If you do have a graph of it, you can kind of see that because there's not a funny jump there, that it seems like logically this is going to work out. Now, how were you taking the one-sided limits on a piecewise defined function? Do you remember? Okay, what we want to do here is think about, I'm very, very close to 50,000, but I'm slightly less than it. So what category am I in? This one right here, where I'm slightly less than it, right? But even though I'm slightly less than it, I'm getting so super, super, super close to it that I'm actually just going to plug in 50,000 right there, because that's going to tell me how the function height is behaving when my number that I input is super, super, super close to 50,000, okay? That seems a little weird because I told you, don't plug in the 50,000 in this category, but now I'm saying plug in the 50,000. Hopefully you understand where I'm coming from here, okay? So this is the limit as x approaches 50,000 from the minus side. So we're evaluating this middle function at a height that's very, very close to this point right here. And if you plug in the number 50,000 right here, you'll get 1,000 plus 0.15 times 40,000. And it turns out that's going to be 7,000. Okay, so that was I'll just show you the work here. How I got that number is I plugged in the number 50,000 into the middle tax bracket. Okay, and that's because I'm computing the limit from the left. Now when I compute the limit from the right, now I fall into this category over here, which happens to include 50,000, but doesn't necessarily have to include it for me to do this trick, because you just saw me use that trick on the last one. Okay, so now I'm going to plug in the 50,000 here, and I get 7,000 plus 0.20 times 50,000 minus 50,000. And that also comes out to be 7,000. And because both of these one-sided limits exist and they're equal to the same thing, that's how I can conclude that the original question posed is equal to 7,000, because I did both of these. Okay, so hopefully you're going to get some practice there with the other materials I've provided, and please let me know if you have any questions on the discussion board.